Hello everybody, and welcome to this lecture. So today we will have something to say about mathematical modeling. So here you can see the beauty of life at the moment. And yeah, we want to ask the question, first, what is actually mathematical modeling? So let's switch to the slides. Yeah, I want to embed this question, what is mathematical modeling, into something, from the past. So what are the roots of mathematical modeling? What is the status now, and what can we expect from mathematical modeling in the future? But before we can discuss anything like that, we have to give some basic ideas about what actually mathematical modeling is about. First, a short answer. A mathematical model is a description of an empirically observable system using mathematical concepts and language. What you see when you read something like that is that is a very condensed kind of description. So we have here something like empirically observable. So you see we have to be very careful about what the words are, and that is because mathematical modeling is definitely something that has to do with empirical systems. That means it is something in the real world, something you can observe, something you can make experiments about. So we are concerned about those systems, and in particular those that are characterized as complex systems, but we come to that discussion later. So today we are just focusing on the discussion, what is actually mathematical modeling. Of course, you can also do mathematics without ever touching mathematical modeling. You can do that because most of mathematics, well, at least half of it is pure mathematics, and if you do research there, then you are investigating mathematical concepts, structures, etc., just by themselves without any reference to empirical systems. So this is the very important part here in the answer. We are dealing with empirical observable systems. But, and that is of course what makes it mathematical modeling, we are using, by doing so, mathematical concepts and language. Okay, I think there needs to be a lot of explanations about this. Now, first of all, we know, we have to say a little bit about observations and measurements. This is, of course, one of the big success stories of modern science. So observations have become finer and finer in scale, or larger and larger in scale. So in one extreme, you can nowadays make observations about a large part of the universe. You can use all kinds of radar technologies and telescopes, so you can go very far beyond the reach of the Earth. And in the other way, you can also make more and more measurements, observations with the help of microscopes. So in the life sciences, I think due to techniques like modern microscopes, you have a much better data situation than ever before, since science started. So you produce from these observations obviously data, and I think one of the best known, intuitively known sorts of data are time series. So you make observations in time. You see how a system is evolving, changing in some way. And that is what defines the scientific spirit. Then, after observing the system, you try to understand it in some sense, and the scientific way of understanding is to formulate hypotheses. You will see maybe that's not the only way. Maybe you don't have to spell out the hypothesis. We will come back to that point when we discuss machine learning. But at the moment, for us, science is mostly the art of making the correct hypothesis. So let's go further with this idea. Hypotheses are something you can formulate, of course, not necessarily with mathematics. You can just use natural language to make hypotheses. But there will always be some sort of mathematical structure, even if you are using natural language. What could that be in that context? Well, obviously, since Greek times, ancient times, people have tried to understand what actually you do express when you use the natural language, and already in ancient times people came up with the notion of logic. And the classical logic, of course, is actually a mathematical structure. It is a binary structure, so sentences can have either the value true or false. So this is a very binary choice of the state of the world. Either something is or is not, so that would be the ontological statement, and it can be either true or not true. And as we know as mathematicians, so you would go into Boolean logic if you formulate hypotheses like that. But of course, in mathematics, we have a lot of other choices, and most of them, as we will see in a later lecture, are incredibly good in condensing a whole scientific theory into a very compact form, which is, for example, a mathematical equation. So that is where mathematical modeling comes in. It uses different descriptions that are ready-made inside mathematics. Very often, of course, if you now look at the historical perspective, the development of the mathematical theory and the need to describe certain empirical systems did go hand in hand. There was a co-evolution. This is true, for example, for classical mechanics. So Leibniz and Newton did develop differential calculus in order to describe how bodies would move under the experience of gravity, or later in quantum mechanics, people had to develop certain techniques in partial differential equations, so that people could investigate something like the Schrödinger equation. Now, all of that, for example, partial differential equations, or let's say also stochastic process, which we will discuss in a moment, they all build a large part of mathematics, and here in this context of empirical application of mathematics or mathematical modeling, I call them frameworks. Okay, let's go to the next slide. So what are mathematical frameworks? Well, they are characterized as being having a large theory in the background, a mathematical theory in the background, so you know something about these frameworks after sometimes centuries of investigations, how these structure actually behave in a mathematical sense. So what are examples of mathematical frameworks? Well, surely, we have partial differential equations. That's a very prominent example, because historically, at least, since up to the 90s, early 20th century, all scientific theories in physics have been formulated with the help of partial differential equations. But there are, of course, other areas now. We have definitely to look, for example, at graph theory. You will see that this is related to a kind of static description of a system, which is also a first step in understanding a system. So it's very important to understand or to incorporate the area of graph theory and its extensions. So we will talk a lot about extensions of graph theory. And a very related field, for example, is category theory. Another field I would like to mention is definitely stochastic processes. So the idea is that most of the systems we look at have a stochastic nature, of course. So definitely stochastic processes are very important. And one can say maybe that in most cases differential equations, for example, are just let's say a shortcut of description of stochastic processes, where you neglect the stochasticity of the system in one way or the other. And but that often has also, of course, an advantage in the mathematical sense, because you have more theory at hand to investigate the system, for example. Now, what is the situation here, with respect to hypotheses and scientific theories? So we did say you try to make a hypothesis about a system. If you have a lot of hypotheses that together explain a certain given empirical system you have chosen in a satisfactory way, then you would call this whole bundle of hypotheses a scientific theory. Now the situation is like that. The idea of hypothesis in mathematical modeling is, of course, that you think of your mathematical models as being equivalent to hypotheses. So your mathematical model, in other words, does establish a hypothesis. And as we already discussed, this has certain advantages, because very often mathematical equations are able to to formulate a hypothesis in a very, very compact way. So in some cases, in some successful cases, maybe even a single partial differential equation does establish a whole scientific theory as a single hypothesis. Maybe the best example for that would be the Einstein field equations. Now, of course, you have to make some assumptions, let's say, about the empirical system in order that you can actually apply hypotheses and therefore mathematical models to a certain empirical system. And that is, you need to believe that the mechanisms that govern the empirical system, they need to be they need to be inferable. So you need to be able to detect these mechanisms. And we will discuss very soon how we are going to detect these mechanisms of the empirical system we want to investigate. It is important to say that this possibility of identification of the system, that doesn't mean that everything needs to be determined in the sense that there is a one-to-one relationship. So once you make an observation, you will always see the same thing. It can very well be that there is some kind of random generator, which is the mechanism inside an empirical system. So every observation would maybe give you a different outcome. But nevertheless, you have to, as you do in statistics, you have to look at the ensemble average in that sense, in that case. And then you could still make a scientific theory about the mechanism, even if that mechanism would be stochastic. Now let's go to the black box model, with which we can now discuss in a nice way the relationship between mathematical modeling and scientific theories and the empirical nature of the system. Now you have, as Francis Bacon, for example, famously pointed out, you have to question the the system under consideration. You have to look at it from different angles. And what does that mean for us? Well, in that case, you have to perform experiments. And in the experiments, you would definitely have different inputs into the system so that you can, ask questions. For example, if the system would be completely deterministic and you would always give the same input, you would expect that the system would always give you the same kind of output. But that would maybe not detect all the mechanisms or all the whole set of behavior the system is capable of. In order to investigate that, you need a lot of different inputs in order to see what the system is capable of. So there will definitely usually be a variation, of the input in some experimental setup, and you would then record for each single experiment what kind of output relation we have, and this gives you a clue, or should give you a clue, that's the idea, about the mechanisms that are at hand in the black box. And these mechanisms then, should be, you have to then to create a scientific theory about these mechanisms you are observing. And this would be, in our case, done by a mathematical model. It's now very important to understand system boundaries. When I showed you the black box model, let's go back for a second. We had here the boundary of the black box. So here you would have the black box. And what is this boundary, So if we discuss that, you have to think about the following. What you want to have is you want to infer the mechanisms of a certain system, but what defines the system must be clear. So you will have certain things that are inside the system and you will have certain things outside the system. And therefore any system description will have to have a system boundary. That is just a logical implication. You can, of course, define this system boundary always arbitrary, but this might establish a problem. So let's try to give you an example. Let's say you set up an experiment in a laboratory, and let's say you investigate, for example, a biological entity, some organism or so. So you give it some stimulus, maybe some electric shock. Think of a frog leg. It's a very classical physiological experiment. And then when the electric shock is applied, maybe then the muscles are contracting and the frog leg moves. If, for example, say, evolution would have been such that the light level in the laboratory would change the reaction of the frog leg in the experiment, then the system boundary of the frog leg would not be the frog leg itself. It would actually be a larger thing, because you need to consider the light level inside the experimental setup as well. So maybe the whole laboratory would then create the system boundary. So for example, you would need to close all the windows such that the whole room would be entirely black, and then you would be sure that there is no interference of the background light level to the experimental system, which is in this case a physiological entity. Another example would be you make a model about how the planets move in our solar system. So you have to define the system boundary as being the solar system, and if you make now, for example, a classical mechanical approach, so you would have to apply Newton's laws. You could very nicely compute, and that is of course indeed being done. You can compute the orbits of the planets around the sun, so you can even go back in time nowadays for millions of years, and you know exactly at what time which planet had which position. But is that really a closed system? So in reality it's not a closed system, because of course the solar system is embedded in the whole of the universe, and there are there's a lot of gravitation coming from other sources. And sorry, that's Lola. And these might change, of course, the movement of the planets. So can you really make a system boundary for the solar system? Well, the answer, of course, is yes. You can do that, and the reason is that the gravitation from these outside masses is so low that you can approximately neglect them. So this kind of choice of a system boundary is absolutely acceptable. Now let's talk a little bit about experimental repetition, because this is actually one of the most important ideas for making scientific theories. So, for example, scientific theories very often are assumed to be time invariant. So the idea is, if you make the same experiment, again and again, it should exactly give the same kind of output. If you don't have that, then one of the most important things in science would be violated, and that is that the experimental outcome can be objectively confirmed by any observer. That means if you publish a certain scientific theory and you say it's like that and that and that, then anybody who is interested in that can also make the same experiment based and then make its conclusion based on the same scientific theory, and then your theory should be confirmed. But you can only expect that if actually the theory itself is time invariant, because this experiment by another observer might be done at a much later point of time. So the requirement that you have an arbitrary experimental repetition giving you the same result, this is one of the fundamental assumptions of any scientific theory. And if a certain scientific theory is not having this property, then this is almost always related to the wrong choice of system boundaries, or of course that can also be the wrong choice of the time scale, for example. So things change slowly, making the situation non-time invariant, for example. In this case, you would have to extend the system boundaries in order to keep up with this slow evolution mechanisms in the background. Okay, I think we understand now what system boundaries are and why they are so important in scientific theories. And this gives me a good opportunity now to talk about the goal of mathematical modeling. Well, the goal is that by any means necessary, so also guessing is allowed. That is an interesting case. We will maybe discuss that in a moment. A mathematical model associated with or applied to an empirically observable system with fixed system boundary, so that is a requirement we just discussed, where the input applied to the mathematical model produces the same kind of output as the observable output of the real system after giving it an equivalent input. The latter empirical observations must obey the principle of arbitrary experimental repetition. So what this says, in other words, is that the goal of mathematical modeling is to construct, with the help of a mathematical structure, a kind of equivalent mathematical structure to the empirical structure which is established by the mechanisms governing the system of the empirical system we are observing. Yeah, you have maybe to read it again and digest it. Now, if this mathematical model does have this empirical equivalence property, maybe only in an approximative way. Just think of the example we had with the solar system. So approximately, but not 100% correctly, we can neglect gravitation coming from outside the solar system. So in an approximative way, then we assume the mathematical structure of the mathematical model is equivalent to the mechanistic structure. So this empirical equivalence explains, so if we can establish this empirical equivalence of mathematical models. This explains why mathematical models can be so successful in order to describe the real world. Of course, it would be a huge philosophical discussion now what establishes real empirical equivalence. We will touch that topic a little bit in the next lecture. Now let's go to the next slide. This idea of approximation is very interesting. So historically, I would say many people in the past have thought approximation is not a very good concept for scientific theories. They really had the idea, they can observe nature and they can exactly understand nature. I think the present point of view is that if you do science, you will never see the real truth for different reasons, which we will discuss in a moment. So you never see the real truth, but you might see it approximately, and maybe approximately good enough so that you can manage the system, you can make predictions, etc. How do we achieve to be approximately good to describe the system? The tool we have at hand is what I call the scientific cycle, and I will show you very soon a figure that is making an illustration of the scientific cycle. Now, what we have is that we of course need in any case to compare the output of the mathematical model with empirical data. So that will be of course the major step where theory and empirical observations come together. But very often we have to do some preparation in order to be able to compare data and model output. So here I have to go a little bit into mathematics. So for example, if you have formulated your theory with a partial differential equation, then very often you cannot say much about this object without making numerical simulations of it. And in this case, you cannot directly put in, for example, partial differential equations into a modern computer. Before you can do that, you will need to make a discretization, and the discretization itself will also introduce a certain type of error you make. So there will also be a natural notion of approximation in doing this kind of discretization. So you see, you will have in the end you will have a lot of different levels of approximation in a real world scientific theory formulated with mathematical models. Also very important is of course that inside the mathematical model you will usually have a lot of parameters, and the parameters themselves, they also need to be having a value which is derived as well from empirical data. So you have in a sense here the following situation. You are in the end testing the output of your mathematical model with the help of empirical data, but already before you do that, you also use the empirical data already in order, for example, to estimate the numerical values of parameters. So empirical data will come into mathematical models in different ways. Now let's really go to our illustration of the scientific cycle. So maybe I change the color. And we start here with mathematical modeling. So this will be this part. And as I said, we will use a certain framework, for example, differential equations, in order to formulate the mathematical model. Now, as I said just some minutes ago, we will have to go to the model preparation. This can involve the parameterization of the model. This can involve the visualization of the model. This can involve a discretization of the model. So all of that will be done here in the model preparation part. Now, finally, we will also in parallel have collected some data, maybe in parallel or afterwards, and these data will also undergo a certain kind of preparation phase. Here you can think, for example, of a data analysis. You can think of a statistical technique being applied to go through the data. Raw data very often don't tell you anything. You need certain statistical concepts that prepare the data for a good analysis. For example, like the first moment, looking at expectations and things like that. So that would be that. Now we are ready to compare the two things in this way. So we have now here the comparison box. If you think back to our black box model, this is exactly what's happening. So we have here two different outputs. We have one output from the black box model where we question the empirical system, and we have an output from the mathematical model. And these two things are now compared. Now, of course, the question is, how good is this comparison? So we need to do an error analysis. And this is done in this box. Here we have to define what we mean that the mathematical model is approximating the truth good enough. The truth is not the truth itself, but the truth established by the observations we have at hand. That is also clear and nothing else. If you can define such a threshold, then, and you are below it, then everything is fine, and you can actually say, okay, my mathematical model might actually be good enough. And here I end up here, and then I can use the model for example, making predictions. But if the error analysis gives you the outcome, well, this is actually, that was not good enough, well, then you have to ask yourself, why was my mathematical model not good enough? Why didn't it compare so unfavorably with the output of the black box model based on the empirical system? Well, there are, of course, a lot of different possible sources of error in that. It could have been, as we discussed before, that your system boundary was just, wrong. That would be here, this first case. It could also be, that your observations have been done with the wrong tools, like it said here, the microscope was defect. That is also a possibility which you have to check. So both of these things here, this one and this one, would be related to problems you have with the empirical observation of the system. But of course, there is also the other possibility that your mathematical model was actually wrong. And this can be, for example, that you have the parameterization has gone wrong. So you did use the correct empirical data, the correct measurements, but somehow, because, for example, your model is very high parametric, an optimization algorithm, which is usually used in parameterization, did give you completely wrong parameter values. That is always a possibility. So this would be that. Or, it could also be that the whole mathematical concept you are using was completely wrong and is not able to cover the mechanism good enough, so that in a mathematical sense you can never reach an equivalence, an equivalent structure, both empirical and by the mathematical model. So let's go back to our figure. If the error analysis gives you the outcome that maybe it was not so bad but not good enough yet, then you can make improvements. You can go back, of course, here to the empirical side. You can try to get better data. You can try here to get better parameterizations at that level. And then you change the model in that way. But you keep, of course, for example, the mathematical framework as it is. And then you go back to the comparison step. And then you start again and with the error analysis. So you are back here. And, so here you have a whole cycle, as you can see, that gives you the name correctly of scientific cycle. And possibly then after a lot of iterations, you can again end up here with the correct outcome, which then enables you again to make predictions. So this relation here gives you the scientific cycle. Okay, but as we discussed, very often it can be that you have actually not the right framework. In this case, it's very important to note that you can jump out of the scientific cycle and go back to the mathematical model itself. And you can, for example, use a completely other framework. You can, for example, instead of using a differential equation, you suddenly realize, oh, this empirical system is highly unpredictable. It is most likely having a lot of random generators inside its mechanisms, so you need to use another mathematical description, for example, stochastic processes. And that would very often come to, or it would result into what I call a paradigm change. I think much of the discussion you have, for example, in quantum mechanics is exactly of that kind of sort. People were not used to have random generators that are even dependent on the observer itself in a physical system, and that's why the foundations of quantum physics really had been a paradigm change inside the physical scientific theory. I will come back, but I'm not discussing it now here, to that kind of part of the scientific cycle. And that will be the relation with machine learning, which is an interesting case in itself. Let's discuss a little bit. We have discussed error analysis. Let's discuss a little bit. We have discussed sources of error. So let's discuss a little bit prediction. Prediction is, of course, the ultimate goal of mathematical modeling. You can very often, people are happy with scientific theories that don't give prediction, but somehow just stop at the level of understanding the system in a certain way. But I would say nearly always what you want from a mathematical model is that it makes the correct predictions. That is really the ultimate goal. So let's formulate it. The ultimate goal of mathematical modeling is to make good predictions about the empirical system, which must mean if we give the system a novel, arbitrary, and previously not considered input, so you have not seen this input before, you have not investigated this input before, the mathematical model then can precisely predict the resulting empirical output given an arbitrary number of observations that always confirm the empirical equivalence. So this is of course now again related to this principle of arbitrary repetition of the experiment. And if you are able to do this, then of course you can really be sure that there is this kind of empirical equivalence relationship between the empirical system and the mathematical model. Yeah, we have already discussed paradigm changes, so I'm skipping over that, but please read through it. And we come now to the last part of the lecture, and that of the lecture today, and that is machine learning. So let's go back to the figure we had, the scientific cycle. It has a lot of black lines already, so I hope you can still look at it. Yeah, so you see what I did here is I have here on the left side the typical starting point of mathematical modeling, and here on the right side I have the typical starting point for machine learning, which is more, of course, really is more embedded not in mathematics, but of course in computer science. Now there is a lot of literature and discussion nowadays, of course triggered by the immense power of modern computation, that somehow states that machine learning is a real competitor to mathematical modeling. So we have to understand maybe first what machine learning is. We will do this much better in the end of this lecture series, where in part 3, where we discuss statistics and machine learning techniques. But the most important difference to mathematical modeling is that you don't put any hypothesis into the machine learning algorithm, not like you put into the mathematical model, but you just start with let's say a blank sheet of paper. So you have a very, very high parametric construction, like a neural network, for example, which is able to be trained. So training means you take empirical data and you let the machine now guess by itself, without hypothesis, what the structure of this data implies. And you do this also in an iterative way. So we have training set 1 and training data set 2, 3, and so on. And you will always improve the machine's, let's say, capability to understand the data set, for example, in the sense that it can distinguish between different types of data stemming from different situations. So you have a kind of categorization, or you can even use it to predict so that is also, of course, also the ultimate goal in the application of machine learning to scientific theories, that they can make, like a mathematical model, correct predictions of the system. So in a sense, if that works in reality, this would be a real competition to mathematical modeling. So we don't need to be shy about that. If that would work all the time, it would be and we can make the right predictions, maybe without understanding what we are doing, because the prediction is somehow hidden, for example, inside the parameterization of the neural network. But if we can make the correct prediction, well, why do we bother? Then we have achieved our ultimate goal by other means, and so we don't need to make any mathematical modeling. This is a real possibility. We really have to accept that possibility. Whether it's already true and whether it is true under all circumstances, that's another issue. But I would like to leave it maybe at that. So just look at the figure again. So what we have is, indeed, we can also, as we just explained, we can also just start with machine learning. Maybe let me just erase the previous oops. Somehow it got stuck. That's of course not good. So let's go back, start again. Okay, let's erase again in a second attempt all these black lines stemming from mathematical modeling. Yeah, it's just slow, so I have to be careful. Okay, here we are. And let's look at the scientific cycle from a machine learning perspective. So we would first implement, for example, a neural network. That's always, I think, the best example. Then we would also use another preparation step. So, for example, we choose how we train the neural network, for example, by backpropagation. We also choose the training sets, which are coming from data collection, of course. And we also have, like equivalent to the mathematical modeling scientific cycle, we also have the preparation of the data. And then, we would have these two steps. And then we also alternatively come to a comparison between the machine learning algorithm and the empirical data. And if that is good for all training sets, it can make possibly then predictions. So using another data set which has not been used for training the neural network. This data set still is analyzed by the machine learning algorithm in the correct way, and it even can make then a prediction saying, but if you would yet use even another input which you have not ever used so far, then I even could give you the output relationship for that as well. So you would end up then also with machine learning in this situation. Yeah, that is a real possibility, and of course, as you might know, machine learning is used a lot in a lot of different areas, and it works entirely well in many cases, but of course maybe not in all cases. So think, for example, of machine learning applied to say automatic driving. So it might work very often because it's has been trained correctly, has the correct sensors to measure the empirical system in which it is operating. But then it might make, of course, a mistake, misjudging, for example, what a certain geometric object is, and then possibly, the car will make an accident because it has completely misjudged the situation. So this, of course, might also happen and might limit the ability of the machine learning algorithm. It will, of course, definitely have something to do with the complexity of the real-world system with which you have to deal with. Okay, I think this ends now our discussion for today, and let's go to the summary. So we learned the prominent way mathematical model is embedded in the wider area of scientific theory building. We discussed the black box model of an empirical system. That's a very important kind of illustration, I think. Yeah, we learned about the different goals of mathematical modeling. Here, the ultimate goal, as I said, was here prediction. Then we introduced the scientific cycle, which iteratively tries to reach better and better understanding of the system. So with the scientific cycle, we introduced the ideas, which is not generally believed by everybody to be true, that science operates in an iterative way, becoming better and better with predictions. The better the mathematical model and the better the empirical data are. And yeah, we discussed the challenge nowadays mathematical model has with the, let's say, rise of machine learning. Maybe let me just say that I'm not pessimistic about that. Machine learning has an absolutely good place in mathematical modeling, and the two areas definitely will become one in the future. So I was just trying to give you here a thought that these two are in principle two different ways to establish the mechanisms, or to estimate what the mechanisms in the real world are. But these two things for sure will come together in the future, and I hope I will say more about that in future lectures. So that brings me to the end of today's lecture. I hope you enjoyed it, and yeah, see you next time. So bye.